Okay. On behalf of WITS alumni here in Israel, Telfed, and World Mizrahi, it gives me a great honor and a privilege to introduce Professor Ehud Duchovni. Just a very short bio, because if I had to do your whole bio, we'd spend most of the evening just discussing your achievements and your incredible biography, but a short bio. So, Prof, you're from the Department of Physics and Astrophysics at the Weizmann Institute of Science, and you received your MSc at Tel Aviv University and a PhD at the Weizmann Institute. You started working on the CERN, the European Organization for Nuclear Research in Geneva suburb, and TESO experiment, which discovered the gluon. Then moved on to the CERN UA1, Underground Area 1, where W and Z bosons were discovered. After that, you worked on OPAL, one of the major experiments at CERN's Large Electron Position Collider. OPAL studied particles and their interactions by collecting and analyzing electron position collisions. And as a result, the number of generations in the nature have been fixed at 3. In the last 15 years, you headed the Weizmann team. They worked at the CERN Atlas. Collaboration with the Higgs boson has been discovered. In between which, you headed the Weizmann team that joined the Exxon experiment that searches for dark matter. Exxon operated at the Italian Gran Sasso National Laboratory. It's a deep underground research facility featuring increasingly ambitious experiments aiming to detect dark matter particles. Now, your presentation tonight, the talk that the heading is The Dark Side of the Universe. And dark matter is a form of matter thought to account for approximately 85% of the matter of the universe. Currently, it cannot be detected. So, Prof, before I introduce to Doron Klein, who's the head of Telfed, South African Zionist Federation here in Israel, we so look forward to you shedding some light on your topic, the dark side of the universe. But I want to just hand over to a very close and dear friend of mine, Doron Klein, who's the head of Telfed.
Thank you, Les. And it's always great to be together with you at these wonderful events that the alumni and Telfed and Mizrahi organize. As you said, to help enlighten our community. And anything that brings people together and make us understand more of our amazing universe can only just help to make us better people, to make our society a better place, is to appreciate the wondrous place that we live in. So I wanted just to say thank you very much to you and to Larry and to Professor Duchovni for joining us this evening. We're steering towards the Festival of Hanukkah, which is the Festival of Lights. I think it's a great time to talk about the dark matter of the universe. So you might understand the Festival of Light a little bit better and appreciate the light that we have. And I just wanted to encourage everyone to have a look at the Telfed website. We have virtual events every week for free. So if you're not getting the Telfed newsletter, then you can just let Les know, and he'll pass on your details to Telfed, and we'll make sure that you're part of the great virtual community that we built during the COVID-19 pandemic. We can't get together and share the light physically, we share the light virtually. So thank you very much, everybody, for joining. I just want to tell you that just this week, 22 new Olim arrived from South Africa to bring more light to Eretz Israel. The Aliyah is continuing from South Africa, continuing to bring and spread light to our community. And I hope that they also will soon join our virtual events. So have a wonderful evening. Toda rabba, everybody, for joining. Thank you to the Professor for sharing of his knowledge. And Erev Tov Kulam, Hanukkah Sameach.
Thank you so much, Doron. And I just want to also mention, I want to take this opportunity to thank my very close and dear friend, Larry Pfeffer, for organizing and helping to organize this event tonight. Larry, we really appreciate it. So Prof, before you start, Am Yisrael, we are Or Lechol HaGoyim, we are light unto the nations. And it's, as Doron mentioned, it's extremely appropriate that he's speaking about this topic coming up for Hanukkah, where we light the candles that illuminates the world and shows the emes. So without any further ado, I hope you're going to be shedding a lot of light on this subject, the dark side of the universe. So without any further ado, our esteemed Professor Ehud Duchovni. And Prof,
it's on mute.
Yeah, unmute.
Well, that's a good way of starting giving a talk. I wanted to thank everybody here and to thank in particular Larry, a dear friend of mine. And let me try and share the screen and see that we can go on. Okay. So, I cannot control it. Oh, wait. Okay, I think it's working. Okay. So I'm facing basically two challenges today. One challenge is to explain what dark matter is, how we came to to think about it and what we know about it. And the other challenge is to do it via Zoom, which is very difficult because you cannot see the others. You cannot feel where you miss the audience. And what I'll do is I'll stop every now and then and I'll take questions. Some questions I'll answer, others I'll keep for the end, but that would hopefully allow you to stay in contact. I'll start by explaining planetary motion. That's important because the first evidence for dark matter comes from something which is equivalent to planetary motion. Then I'll show where Newton and Einstein seems to fail, and I'll commit something which is considered as a suicide attempt in talks. I'll show equation. Hopefully we'll survive that. Then I'll go and I'll show other curiosities of the universe, a few other effects, and I'll wrap it up in a sense later and show that all these features can be explained by assuming the existence of one thing, namely dark matter. Then at that stage, we should have some idea what dark matter is, and I'll discuss a little bit how we search for dark matter. And then I'll touch something which I consider to be a magnificent mystery, and that is that if you go from the biggest thing, from the cosmos, to the smallest thing, to the particle physics, namely you jump 45 orders of magnitude, namely a number which is 1 with 45 zeros, then in particle physics you find a very good motivation for dark matter. So somehow the biggest and the smallest combined forces and why can't I switch transparency? Oh, so I can't start without saying a few words about contemporary physics. I believe that this is probably the greatest achievement of human intelligence. We managed to do things that were considered completely impossible 30 or 40 years ago. And now we understand basically the universe from about a millionth of a second after the Big Bang. And don't ask me what happened before that. We don't know. It's not yet within the reach of science. If we cannot do experiment and we cannot measure, then we can only hypothesize, and that's not science. So we know what happened about the millions of millions after the Big Bang till now. That's about 14 billion years. And we know things from the very small, some objects which are 10 to the minus 18 meters. Again, that's a 0 with an 18 zeros and then a 1 meter, till the size of the universe, which is 10 to the 27. I mean, again, 1 with 27 zeros. So it's a vast area, and everything fits together, and everything is whatever we can predict and test fits. So it's an amazing achievement. Yet we understand very clearly that our understanding is still lacking. There are lots of things that we don't understand. There are quite a few major issues that we don't understand, and one of which is indeed dark matter, and we'll try to focus on that one. So how can we study something that we can't see, or alternatively, if I had to put this because it reminded me of Peretz putting his lead on leaving the landscapes on his binocular a few years ago. So how can we search for something that we can't see? So let me start 2,500 years ago, or roughly like that, and with Aristo, and Aristo told us that the Earth-centric theory, the Earth is in the middle, and everything rotates around the Earth, and everybody was happy with this for more than 2,000 years, or almost 2,000 years, and then people. Not that many people, but started looking, oops, no, I want that. This is something which I saw only when I prepared this talk. This is the planetary motion as it's seen from Earth, and it should start playing. Here it comes. So you see, for instance, I don't know whether you can see my cursor. This is Mercury, and this is Venus, and they move. Mercury moves the fastest, and the further stars, the heavier one, Jupiter and Uranus, and all these move very slowly. And this is the picture that you see when you look at the sky. It's practically never shown. And out of this terrible picture, Copernicus, Bra, Kepler, and Galileo cooked up the idea that the sun is in the center and the planets are surrounding it. And that explains this very, very complex picture. Now that was the observation, and that's not enough, because then came Newton with his brilliance, and he offered also a universal explanation. And that's very important, the two words. Universal means that his explanation holds true everywhere. It's right here, and it's right in the States or in South Africa, and it's right also at the other edge of the universe. And again, I told you that I'm going to commit suicide. So this is the famous Newton equation for the attraction between a body with a mass m1 and a body with a mass m2. They attract each other with a force, and that's everywhere. I'll let you read it, because it's great. So the reason the church was so strongly opposed to what Galileo and the others had to offer, I don't believe that it is because the sun became the center of our universe and not the earth. I think it was more the transition from the notion that The truth is in the scriptures, and if you want to know the truth, read and study the scriptures. And we move to modern science, which says, first of all, observe, think, and come to some sort of hypothesis, then predict. And once you have a prediction, then you can carry out a test. If the test checks, then you manage to understand something. If the test doesn't check, then go back, think again, and try to come up with a different hypothesis. And you'll see this in action in this talk. That's another picture that is rarely shown. Here you see the planets rotating around the sun. And this is done right, namely the velocity in which each planet moves is the correct one. You can see that Mercury in the center, which is closest to the sun, is moving extremely fast, and the planets which are further out are moving very, very, very slow. And that's important. That's brings me to this transparency. And here, I don't only show an equation, but I'm gonna use the equation. As you can see at the top right, I can't see it, so I'll move the, okay. As you can see, the equation tells you that the velocity with which the planet is circling around the sun is proportional to 1 over this funny signal is square root of r. Namely, look at the table, the Earth is at a distance of what we call 1 atomic astronomic unit from the sun. So the square root of 1 is 1 and the velocity is 1. Jupiter is about 5, let's say 4 units away from the sun. So the square root is 2, therefore it moves at 1 over 2, namely half of the speed of Earth around the sun. And Uranus, I think, is at about 16, this distance which is 16 times bigger than the distance of Earth. Namely, the square root is 4, and it moves at a quarter of the velocity. So the further the planet is from the sun, the slower it moves. And that's very important. Now we go from the solar system, we go to the next bigger structure in the universe, namely to our Milky Way. Our Milky Way, you can see it beautiful in this picture. This is a reproduction of how it looks. It's what we call a galaxy. It's a spiral galaxy. You can see the sort of lines. It contains about 100 billion stars. And the sun is just a simple star in this galaxy. It looks like that in terms of the spirals, and this is the sun. Or if you like, you can see the sun sitting here. And the whole object rotates around the center. Now in the center, there is something which is sort of like a mega sun. There's a huge black hole at the center of our galaxy. Its mass is about 10 to the, it's about 4 million times the mass of the sun. So it's huge. But in terms of the whole system, it's not that big. We moved to 100 billion stars, and the center object became only 1 million times heavier. So it's not as dominant as the sun. But still, the whole thing is rotating around the center, and each rotation takes about 200 to 250 million years. Now we can apply the wisdom that we acquired and the equation that I showed you to the Milky Way also, because there are objects outside of the Milky Way. Like, do you see my cursor, by the way? Okay.
Yes, we do.
Right. So there are objects which are outside of the galaxy. You saw that the galaxy extends, and then the density of stars drops fairly steeply, and then it looks as nothing. But if you look with a good telescope, there are still some stars and some gas clouds and all objects like that outside of the galaxy. And this is one object like that. And it will also rotate around the galaxy. And I can talk about the velocity by which it rotates the center of the galaxy. But now it looks at the first moment that it's as if this is a much more difficult problem, because the mass is distributed in the galaxy in an uneven way, and you don't know what to do with it. But physics tells you that you don't care about the distribution. You can just accumulate all the mass into one point at the center of the galaxy, and that should be okay. That would give you the right answer. So now we know that all the mass of the galaxy is here. We know what the mass is because there are about 100 billion stars, and the sun is an average star. So just take the mass of the sun and multiply it by 100 billion, and you get roughly the mass of the galaxy. Multiply it by 2 or 3 just for safety. So we know the mass, and we can, why does it again? Never mind. And now we can plot the velocity as a function of the radius, and we know from the equation that I showed that the velocity should drop. And once you've done that, you can go and measure. And when you measure the velocity, you see a disaster like that. What you see here is, this is the expected velocity, and this is the measured one. So further away objects which are outside of the galaxy, but still are rotating around our galaxy, are rotating at a velocity which is tremendously higher than expected. And how can we explain that? I mean, this is not foreseen neither by Newton's physics nor by Einstein physics. It's something that is completely surprising. Remember our equation. Equation tells you that the velocity is inversely proportional to the distance, but it's also proportional to the mass. So if you want a higher velocity, you should put higher mass inside. So we can understand this very high velocities if we assume that the mass inside is much, much higher than the mass that we see. So I told you first, take the mass of the sun, multiply it by 100 billion, and you get the mass of the galaxy. Not true. If you look at that, you should add huge mass, much more mass than the visible mass. And where is this mass coming from? Now, we don't see anything. We look at the space near the galaxy, inside the galaxy, outside of the galaxy, and we see nothing. So there must be something which is invisible. Invisible, it means that it doesn't interact with light, which means that it doesn't interact electromagnetically. So there's something which is invisible, but still it has mass. Because this is a very important point, let me show it in a different way. So this is the body of the galaxy, the green object, and we expect the velocity to drop. Rather than dropping, it's flat, or as you saw, it's rising. I mean, we've measured the rotation curve of hundreds of galaxies, if not more, and practically all of them behave like the one I show here. Behave like either like a flat curve or one that even goes higher. So where did we go wrong? And let's stop here for a second and see if somebody wants to ask a question.
If there's any comments or questions from our audience, we have a lot of participants. So you're all welcome to ask Prof any, or to make any comments at this stage.
Ehud, how do we estimate the number of stars in our galaxy?
We practically count them. You take a piece of sky, you aim a good telescope at it, and you count the number of stars, and then you know that in an area of whatever square arc seconds, you got a given number, and then you can continue, and you can calculate it. Then, like you can measure the number of hairs on the heads of a person. You take a square centimeter, measure it, and then calculate the area of the head.
Well, how can we do that? If I understand, the galaxy is basically flat. It's an approximation, right? So it's flat.
No, it's a pancake shape, and the diameter, if I remember correctly, is 100 light years, and the thickness is 30 or so. So it's not a flat, but it's pancake shape. Okay. So you can reconstruct it by just measuring different. You aim your telescope in one direction, and you aim your telescope in another direction, and by doing that, you can reconstruct the galaxy. You can reconstruct the shape of these spirals. You can do everything.
How do we estimate the distances?
Pardon?
How do we estimate the distances?
It depends on the you estimate the distance depending on the distance. Now, if the distance is not too big, then you have this technique of parallax. The Earth rotates around the sun with a radius of 150 million kilometers. So you observe a given star in the summer, and you observe it in the winter once you've moved 300 million kilometers. So it's like when you open and close one eye and the picture shifts, you can see a small shift in the direction of the star. So that technique is good up to, I don't remember. I'm not an experimental astrophysicist, so I don't know these numbers, but this is good for a substantial part of the galaxy. Then there's, for instance, another technique. There is a correlation between the color of a star and the amount of light it emits. Stars are fairly boring objects. They follow a very well predicted curve during their lives. So you see a star, you know that it's, say, a red, you know that the amount of light that it should radiate is whatever it is, and then you know how much it radiates, and you know how much you get. So from that you can deduce the distance. Another technique is there is this. This is better at much higher distances, but there is what we call supernova 1A. That's a standard explosion, and again, we know exactly how much light will be emitted with once the star explodes. And then you know how much light is emitted, you know how much you see. It's like when you see a torch, if you see it dim, then you know that person holding the torch is far away. If you see it strong, you know that that person is closer. Any other? Okay, so I'll continue and I'll stop a little bit later and we'll take more questions. So our picture is, I told you that there's mass which is missing. So the picture that we cooked up is this one. The galaxy is made out of the luminous part, which is the purple or whatever it is, pink circle. And there is this other stuff that we call for the moment dark matter, and I'll get to what it is. There is this dark matter which has mass and a substantial amount of mass, and it's spread everywhere. It's also denser at the center, but the density goes is getting lower and lower, much slower than the stars. So the center is stars, and then there's dense dark matter, and then there's less dense dark matter, and there is quite a bit of mass, more mass, about 10 times the mass of the galaxy, 10 times more than the mass of the stars is in the dark matter. Or in other words, most of the mass is in dark matter. Now, this is a hypothesis, and we need support for that. This is a picture of the universe, basically. And here, the reconstruction is also done. It's much harder to do it, but still, it can be done. And I've put here an arrow, pointing at this. This is not a star. This is not a galaxy. This is actually a cluster of galaxies. And a cluster of galaxies may contain also as much as 10 to the 11, 100 billion or so galaxies. And actually the beginning, the term dark matter was coined later, but the beginning of the story of dark matter starts with a Swiss guy by the name of Fritz Zwicky, and he studied clusters of galaxies. And what he saw is exactly what I just mentioned concerning the Milky Way, namely, in cluster of galaxies, the galaxies are circulating around a common center. And what he saw is that there's not enough matter to keep the galaxies together and to keep them rotating. Matter is missing there. And he suggested that there is some sort of a dark stuff there that we cannot see but has huge mass, and that would keep the galaxies in the cluster together. You probably heard about the fact that Einstein suggested general relativity, and what the theory says is that mass bends or distorts the fabric of phase-space, and for that reason, light, when it goes near high mass, it bends a little bit, like light in a lens. So suppose there is a star here. This is a very, very far away star. And suppose we are sitting here. And suppose there is a galaxy or a cluster of galaxies almost at the line of sight. Now, the mass, the light, this object radiates light in all directions. So for instance, a beam of light that goes in this direction gets bent by the mass here and reaches our eyes. Now, the light comes like that, so we think that it came all the way from this. So this is sort of a reflection of that point. And there's another reflection here. And so the picture becomes more complex, let's say. In 3D, what you see is that this is Earth. This is this galaxy that is the length, the gravitational length, and this is a far away galaxy, or usually it's a quasar object that radiates a huge amount of light. And what the person here on Earth sees, that light comes from all that circle. This point in the center is reflected onto a ring. I'm not sure that this is a real, I mean, I found it in the pictures of Google, but I find it hard to believe that this is a true picture, but this is a true picture. This is what we call an Einstein ring. There's an object, I think that this is the object that gives off the light, and the light is scattered in such a way that we see these fractions of a ring. Now we know that this light and this light and this light is the same, because it's like the finger print of each star. The light is a spectrum, and from the spectrum you can identify the source, and the spectrum of light that you see here and here and here, all along these things is exactly the same, and it's identical to the one that you see here. So we know that what we see is gravitational length. Now we can calculate what the mass of this galaxy, or it's a cluster of galaxies, is. And again, the mass that we get is not enough to do this lensing trip. We need to have about 20 more mass to get the lensing done. So that's another indication that in these are further away cluster of galaxies, and we see only small part of the mass. Most of the mass is invisible. So we have by now we have already three arguments. There's the galaxy rotational curve, including our own Milky Way. There's the rotational curves also of galaxies in clusters, and there is the gravitational lensing. All three of these call for something which has mass but is not visible. Now, so that's the picture of our galaxies. Hot gas, namely stars, in the middle, and dark matter at the outer part of it. Now, suppose two things like that collide, two galaxies. So here is a simulation of what happens. The dark matter is unaffected by the collision, but the stars, they act with each other, they collide with each other, and you get basically the dark matter of one galaxy continues moving without being changed. The dark matter of the other galaxy moves in the other direction, and the stars that attract each other, that are in much stronger interaction, they form some sort of, I don't know, some shape. Now, this is a nice hypothesis. If you look at the simulation that has been done, then there's a galaxy that is going to come from the left. Here it comes, and it collides with this galaxy. And the output should look like that. And when you look at the sky, you see this picture. You see here the hot gas, the center of the galaxies. You see here the dark matter. Again, we identify this by gravitational lensing and other tricks, but and you can see that this looks exactly like what we expected from this simple picture, that the galaxy has a core of stars and which is embedded in a pool of dark matter. This is called the bullet galaxy. I think that is the only picture that we have up to now of a collision of galaxies. It happened a few millions years ago. Let me return to this picture. I told you that this is reconstruction of the universe, and these are clusters of galaxies, and you can see that the shape is very, very strange and sort of elaborated. But the Big Bang started as a hot soup which was homogeneous, and the hot gas and whatever was there was speeding away, and it was uniform. So how come that we start with a uniform situation and we end up with such a wiry, I don't know how to call it, structure? Again, it's hard to understand, and I cannot well, I can explain it a little bit. Yeah. We assume, I'm jumping a little bit, we assume that the dark matter is made out of particles which are relatively heavy. So they serve like when droplets are formed, there is always something at the center that is the condensation, I don't know, initiator, whatever you call it. So these WIMPs, okay, I'm jumping, but the dark matter particles made this picture possible. So that's another very strong indication for the fact that there is dark matter. The fact that we start with a soup, a homogeneous soup, but we end up with something as horrible as this. Okay. The last piece of evidence is this picture. This is the temperature of the universe when you look at in all directions. Now, don't get excited about the differences that are blues and yellows and reds. The difference between blue and red is about 1/10 of a thousandth of a degree. So these are very, very, very small differences in the temperature. The temperature is what you see at empty space, and it's about, it's almost absolute zero. It's 3 degrees above the absolute zero. And there are these small differences. You can mathematically work out from the differences, you can work out a lot and get lots of information. Again, the calculation is far from being trivial, but what it tells you is that 70% or so of the universe is made out of something which you call dark energy, which I didn't mention up to now, and I won't mention it in the continuation. It's something that we completely don't understand, but it is responsible for the fact that the universe is expanding, and the rate of expansion is getting higher and higher, which is something very strange that nobody expected. About a quarter of the matter, of the mass of the universe is this dark matter that we spoke about in the last 45 minutes or so. And only 5% is the matter that we know. The atoms and galaxies and stars and what have you. It's only 5% of the mass of the universe. So actually, most of the universe is unknown to us. So we have 6 pieces of evidence that all can be explained by the assumption that there is dark matter. The galaxy rotational curve, the rotational curve of a cluster of galaxies, gravitational lensing as we mentioned already, and then there is the bullet galaxy and the picture of its collision. There's the structure of the big structure of the universe with these sort of wires extending from one end of the universe to the other, along which there are lots of clusters of galaxies. And then there is the anisotropy of the cosmic background radiation, which I showed right now. So let's make another stop here and see if there are comments, questions, refutations.
Professor, when from the Big Bang, what did the universe expand into?
I'm not sure I understand the question, but it expands into the universe that we know now. It had a very peculiar phase in which we call it inflation, in which it inflates very, very fast, faster than the speed of light, which is possible because it's not that something that was moving faster than the speed of light, it's space itself expanded faster than the speed of light. So in the picture that I showed at the beginning, you can see there's a narrow thing and then it expands fast. So that's the inflation period. Again, the inflation is relatively a new idea and very strange one, but there are quite strong evidence that it's true.
Is it too simplistic to say, therefore, it created its own space into which to expand?
Yes, I mean the whole Big Bang is, I mean it's unlike we are used to say something cannot come out of nothing. Something came out of nothing, probably. Yeah. Again, we don't know what happened there, whether it was quantum fluctuation, some claim, or Almighty God, that is other claim. I don't know.
Okay.
Out of the reach of science, at least now. But okay, any other?
I have a question. Ehud, I understand what it means that the rubber band expands. What does it mean that space expands? Space is a thing, according to the way physics sees it. It has physical attributes, dimensions.
It has size. I mean, again, it's hard to say because to explain, because one lesson is that you learn is that our intuition is rooted in our experience, and we live in a centimeter to meter like universe with a temperature of 300 Kelvin and speeds which are slow. When you go to extremes, when you go to super high speeds, then things get changed, and special relativity starts to dominate, and time, for instance, flows at different rate. When you go to very cold situation, you get superconductors and superfluids. When you go to supermassive things, you get general relativity. When you go to super small things, you get quantum mechanics. So our intuition is unable to cope with these notions. Now, here you go to the combination of few extremes of that sort, and our intuition is worthless. So what you do is you write the equations, and as long as the equations are self-consistent and they give you meaningful results, then you continue to use them. So this inflation is inflation of space. You sort of write the matrix of space, and then you apply on it some sort of an operator that makes it bigger. I cannot explain it better than that.
Another question. How do we know that when two galaxies collide, that the dark matter doesn't combine only the galactic material? Detected by gravitational observations.
Yes. There are four forces that we know in nature. There's the electromagnetic force, and stars would interact with each other via the intermagnetic force. There's the nuclear force, which is responsible for atomic explosion and for instance, the creation of energy at the center of the sun. And again, stars would interact via the strong force. And there is the weak interaction, which is much weaker than these two, and it's responsible for radioactivity. And again, stars are susceptible to such an interaction. Dark matter, as in the hardcore version of dark matter, it interacts only gravitationally. Gravitation is unbelievably feeble. It's about 40 orders of magnitude weaker than the electromagnetic interaction. If you take two electrons, for instance, and you calculate the electromagnetic or electrostatic attraction or repulsion between them, and then you calculate the gravitational attraction between them, then you will see that the gravitational attraction is 40 orders of magnitude weaker. For that reason, dark matter is practically non-interacting object. It just goes without seeing anything. You have another example. There are particles that we call neutrino. Neutrinos are susceptible to weak interaction only. And they come from the center of the sun as if the sun does not exist. They go through Earth as if Earth does not exist. And they would go till the other end of the universe through stars and galaxies and what have you, and they will very, very, very randomly interact. They do interact a little bit, but the probability of an interaction is unbelievably small. So the same holds true for dark matter. It doesn't interact. Whereas stars, well, you know, you take two rocks, you bang them together, you see that they interact. Another urgent one, or we continue? Okay, so we continue. So we have these 6 reasons to believe that there is dark matter, and then the question is, what is it? And it can be everything. It can be some sort of a soup, sort of a homogeneous, structureless entity that fills up space. It can be even a property of space. But again, there are lots of ways of getting out more information from these 6 phenomena, and the conclusion, the sort of the consensus today is that dark matter is made out of small particles. They are heavy, their mass can be as light as a proton or as heavy as a uranium, roughly in that range. So it's a known mass in a sense. And as I said, they're interacting very, very weakly, either only gravitational, or maybe here the word weak is a bit confusing because it's also a name of an interaction. So it can interact weakly, namely via the weak interaction, via this particular interaction, or just do it very feebly, let's put it that way. So we call them WIMP, for weakly interactive massive particles. And that became sort of a synonym to dark matter. So how do we search for WIMPs? There are many, many ways of searching for WIMPs. I mean, probably one can fill up 100 hours of discussion. Basically, there are two categories. One is the active one. In accelerator, we try to generate WIMPs. It's a problem because if you generate WIMP and you cannot see the WIMP because it doesn't interact, so you generate something that you cannot see that you've generated. So how can you know that you've generated something that you cannot understand the problem? So there are tricks to bypass that, and we get meaningful results from accelerator physics. And there is the passive way, and this is let a WIMP interact with matter, and let's try to see whether we can see the outcome of such an interaction. Now, I told you that WIMPs are weakly interacting, which means that they interact very, very weakly. So, but still they interact. So if we prepare, say, a target of one tone, one metric tone, then we would expect few interactions per year of these WIMPs on this target. And when such an interaction occurs, again, it depends on the mass of the WIMPs, lots of assumptions. But when something like that occurs, then usually there is a small speck of light, a very, very feeble signal of light. So now we know how to search. Let's build a target and see where it emits light. So to build a light-proof container that no external light would come and spoil the measurement is trivial. To build detectors that are sensitive enough for these very, very small light signals, relatively easy. The real problem is the background, because there are particles that are coming from above, from the outer space, and we call them cosmic rays, and they go very energetically through everything, and when they go through, say, any given target, they may give up a little bit of light. There is natural radioactivity, and we all live in a radioactive pool. So natural radioactivity would give, again, small signals of light. So the real problem here in trying to find the dark matter in that way is to reduce the background. So if you drive from Rome to Pescara, actually, if you drive from Pescara to Rome, the entrance is in that direction, then you cross a tunnel, which is about 10 kilometers long. And it goes under the mountain, and on top of it, it's an important mountain because at the top, there is a villa. In this villa, Mussolini was kept as a prisoner by the Italian, and toward the end of the Second World War, and the German with Otto Visconti, I think it was the name of the guy who did it, managed to kidnap from that villa. So that's about 2 kilometers up from this point. So you reach this junction under the mountain, and there's a huge metallic door here, and this is the opening to a huge, well, big underground laboratory. Here you see a sketch of the laboratory. These are the 3 experimental halls The biggest one is, I think, 300 meters from edge to edge, and it's about 20 meters high. And that's how such an experimental hole looks like. And in one of these 3 experimental holes, there is an experiment which is called xenon experiment. The name is because the target that we use to look for dark matter is liquid xenon. Xenon is a gas, it's a noble gas, and when you cool it to 106 degrees under zero, minus 106, then it condensates into a clear liquid. Fairly expensive, it's about $4,000 per liter. So this is the counting room with all the systems that we need in order to keep the experiment running. You can see here all kind of things. We cannot see the espresso machine, which is the most vital one. And this is the experiment. This is a huge tank, which actually was built by us at Weizmann. And the tank is full of extra clear water and a system that looks for light in the water. Now, this is not looking for dark matter. This is looking for background, because if we see background in the water, then it is likely that we will have also background in the xenon. So this is, for instance, if a cosmic particle comes from above and impinges into the water, then it may also go through the xenon container and contaminate it. And in the center, there is this xenon container. You can see it in the next picture. This is the container. You can see here down, these are the light detectors. The thing here is to keep the electromagnetic field uniform. And you see that the guys here are wearing all this equipment. This is before the Corona time, because it needs to be super, super, super clean. And that detector is, it went through quite a few stages. It started with a 10 kilogram liquid xenon, then we moved to 100, then we moved to a 1-ton experiment. Now we're doing a 3-ton experiment, and we'll probably end with a 10-ton experiment. And as I told you, it's the number of interaction is per year. So that thing is standing there and waiting for a WIMP to come and interact inside it for quite a long time. So for instance, we published a paper about 100 days of run and another paper about 227, I think, days of run. And the result, this is typical result. You can see, oops. You can see the black dots are sort of background. We know that they are background. The purple here are also sort of background. And these the ones with different colors, these are events that may indicate the existence of a WIMP. You can see that there is, say, if you take this event, then there is 50% probability that it's a neutron. If you take this event, then there is a 50% probability that it's a background due to surface effects. And this one is the one that looks most WIMPish. There's almost 50% probability that it's a WIMP. Up to now, we didn't get any positive results. The conclusion of the last run is that there is some sort of a weak indication, not statistically significant. Now, let me end up with what I promised you, help from the minute world. As I said, particle physics is dealing with the smallest possible particles, the constitutes of the constitutes of the particles in the atom. We have a beautiful theory, which is called the Standard Model, that explains practically everything that we see. It's the most successful theory in the history of science. I don't think that anybody can argue that. And currently, we believe that there are 3 generations. Each generation consists of 4 particles. Altogether, there are 12 fundamental particles. There are some particles that carry force. Namely, how come that an electron that sits here knows that another electron sits there and they repel each other? Something must go between them and tell this electron that the other electron is nearby. So these are called force particles, and there are several such force particles. And the Standard Model also predicts the existence of a new type of particles. It's a different, fundamentally different type of particles. It's called the Higgs boson. It made a lot of noise because somebody called it the God particle, and then people really thought that it has anything to do with God, which is nonsense. It's just a bad name. But the Higgs boson is fundamentally different from all the other particles. And we searched for this Higgs boson for quite a few years, 40, 50 years. And we discovered it in Atlas in our last experiment in 2012. Actually, July 4th, 2012, it was announced. Now, this Higgs boson, which I told you it's very, very strange, must be light. And we measure it, and the light, it's a bit heavier than an atom of lead. On the other hand, we can calculate the mass of that particle. And when we calculate the mass of that particle, it's extremely heavy, 17 orders of magnitude heavier than what we measure. So we have a contradiction. And this is one of the hottest issues in physics for the last, I don't know, 10 years. And it is somehow connected to the fact that why gravity is so weak. I told you that gravity is unbelievably weak. So the two things are connected. So is the Higgs boson light or is it heavy? And why? Actually, we know now that it is light. So how do we cope with the calculation? What's wrong there? We can't find anything wrong. So there are all kind of work around, and the nicest one is that a new symmetry was introduced. Now you need to know that symmetries play a major role in physics. I mean, it's in particle physics. Don't have time to explain, but symmetries are become almost the essence of physics. So somebody invented a new symmetry which allows us to modify the calculation and to make the calculation such that the Higgs is light and the mass, the calculated mass, is also light. So there's no contradiction and everybody is happy. One outcome of this, it's a family of models of this, let's call it theory. One outcome of this theory is that there is yet another particle, which we call the lightest SUSY particle. Fine, so who cares about that? Why do I waste your time telling you about the particle physics and LSP, except for the fact that I worked on that for quite a few years. The reason is that this LSP is the characteristics of the LSP, light SOZ particle, are identical to those of the WIMP, the weakly interactive massive particle, namely the particle of the dark matter. Or in other words, the LSP can be the dark matter particle. And here you get another reason for dark matter. That's the seventh one. We saw 6 in the list. Now there is a 7th one, and that is that particle physics basically requires the existence of dark matter, which is mind-boggling because there, as I told you, there are 45 orders of magnitude between the physics of cosmology and particle physics. And to find that one theory that deals with super small things has something relevant to teach the other one is, I think, fantastic. So to conclude, I think that physics, modern physics, is a tremendous success story. It still suffers from a large number of problems. I listed here a few. For instance, the universe. I mean, we begin that at the we believe that at the Big Bang, there was an equal amount of matter and antimatter. They're symmetric to each other. So why you cannot generate matter without generating antimatter? On the other hand, today in the universe, there's no antimatter, not at all. I must tell you the joke. The joke is that scientists are excited because they discovered a section of the universe which is made out of antimatter, and they see there an anti-galaxy, and in the anti-galaxy they see an anti-star. So they build a huge telescope on the moon, and they aim it at this anti-star, and they see that in the anti-star there are anti-cities, and in the anti-cities they see anti-Semites. And I cannot even see that if you're smiling. So coming back to this transparency, you scared me.
Good joke, Ehud.
It's useful when I talk to Gentiles, I always tell it. So why they...
Is there also an anti-fa in the anti-galaxy?
Empty what?
Anti-fa, you know, the ones who created all the violence recently in America.
Oh, come on.
Anti-fascist.
Yeah, no. Okay. Antifa, yeah. That's it. Changed the joke. Fine. So we don't understand, for instance, why there is no antimatter. We don't understand why the Higgs is so light. I mean, we have this theory, but it doesn't explain it well enough. We don't understand what dark matter is. We certainly don't understand what dark energy is. We don't understand what there are 3 generations. We don't understand lots of things. Now in 1892 or 96, I'm not sure, Lord Kelvin, the guy who discovered the electron, told the young physicist, hey guy, physics is over. There are only 2 small clouds in the sky of physics. Basically, don't touch it. The 2 clouds were radioactivity and the photoelectric effect, which gave rise to quantum mechanics and special relativity. So there were huge clouds with unbelievably storm with them. Today, there are quite a few clouds, as I mentioned here, and physics is therefore alive and kicking. Thank you.
Well, so the Prof, I really want to thank you. Your talk has been very illuminating. It really has. It's been really wonderful. And for our viewers out there, because we have a lot of participants, if there's any concluding remarks or can people still ask final questions? Prof, you okay? you could take some questions if anybody has a few comments, questions to ask.
Sure, if they survive till now, yeah, they deserve it.
So if any of our participants want to comment or make suggestions or ask any questions, the floor is yours.
Can I ask a question?
Sure, Rav, absolutely.
The way what I was understanding was that, let's say, looking at just our galaxy, so the planets that are closer to the sun are moving faster, and the ones that are farther away are moving slower. Then once you get outside the galaxy, then the objects that are moving around moving faster because of the dark matter, correct?
Yes.
So, but why doesn't, if the dark matter is so much more matter than everything else in the galaxy, then shouldn't it cause everything that's on the periphery of the galaxy to be moving faster than things that are closer to the middle?
It's a good question, and the answer is because it's non-interacting. Actually, the dark matter itself doesn't move. Actually, it's almost at rest. The objects that are at the outskirts of the galaxy are moving, and they move fast because they see all the mass. They see a mass consisting of the stars and huge amount of dark matter. For that reason, they need to move fast. But it's not that the dark matter is moving.
The dark matter should make everything come towards it, no? It should have a more powerful gravity than the center of the galaxy. Like, why would we be orbiting the sun instead of orbiting the dark matter?
No. Because it's a question of scales, namely the amount of dark matter in the region of the sun where we live is, I wanted to do it, to calculate it, and I forgot. But it should be something like 1 billionth of a gram per cubic meter. So if you look at it, it's practically nothing, 1 billionth of a gram in a cubic meter. I'm not sure that this is the right number. That the right number is about a third of a GeV in a cubic centimeter, but it's 1 billionth, so roughly like that. So the density of dark matter is very, very, very low. And for that reason, it doesn't affect the motion of stars around the sun. But if you look at the volume that is being filled with that low density, then the distance from here to the center of the galaxy is about 30,000 light years. And all these 30,000 light years are filled up with dark matter with that particular density. So it amounts to a huge amount of matter. And as I show a plot where the circle shrunk, and I told you that you can consider as if all the mass is at the center. So you can take all these huge volume of dark matter and assume that it sits at the center of the galaxy, then it would affect the stars that circulate the galaxy, but the effect on the solar system is very, very small. Actually, there is an experiment that tries to measure it, and they see an effect, and I'm pretty sure that they're cheating.
Isn't the positron antimatter? Because based on what I understand, if the positron meets an electron, they annihilate.
Positron is the antimatter. It's the anti-electron, yes.
Isn't that considered antimatter?
Pardon?
Isn't that considered to be antimatter?
Yeah. Positron is the anti-electron. It's antimatter. Yeah.
No, because you said that there is no antimatter. There is no questions about antimatter.
Sorry, maybe I was was not careful enough. Of course, we can generate antimatter at lab. Actually, the biggest producer of antimatter is CERN, is the experiment there in Geneva. B, antimatter is being produced every now and then in the universe. For instance, at the center of our galaxy, around this unbelievably big black hole, there are processes that give rise to positron productions. But the amount of antimatter in the universe is negligible. It's to see an anti-electron or positron is very rare. So it's not that there are anti-stars and anti-galaxies and stuff like that.
Question, why is the
Anyway,
standard model?
Pardon?
Sorry, finish. I'm sorry that I interrupted you. Go ahead.
The dark matter is in a funny way, the anti-particle of itself. And that is one of the way we can limit. Okay, we can sort of get more information about the properties of that dark matter, because we know that when a dark matter particle or when a WIMP hits another WIMP, then they annihilate into photons, and you shouldn't let that happen too easily, because if this happens, then the dark matter would have been disappeared by now after 13 billions or so of the universe. And it cannot be too slow, because then we would have too much of dark matter. So actually it gives rise to something which is wonderful, also some sort of property that looks like a miracle, but it's too difficult to explain.
Why would you say that the standard model is the most successful model? Why is it more successful than the periodic table, for example?
Oh, because it goes much deeper. B, the periodic table is okay. There are atoms with different structures, so they have different properties. The standard model tells you that, for instance, there are conservation laws. Why is energy or momentum or whatever is being conserved in physical processes? So the standard model tells you that it's because of symmetries again. Then you ask yourself why there are forces in nature. How come the electron is attracting a positron or so? And again, the standard model explained the existence of these forces, again using symmetries, and it explains the properties of the forces and tells you a huge amount of information about these forces. There are 100 with the periodic table. So Mendeleev could have guessed that the Eka silicon has got a given mass and a given density and boiling point. With the standard model, you can make hundreds, if not more than hundreds, predictions, and all these predictions are confirmed and checked with the prediction. The accuracy, if a cannon fires a shell to a distance, say, of 20 kilometers, and it misses the target by 50 meters, then they would tell you it's a hit because of wind and what have you, humidity and so on. You cannot aim better than 50 meters or over 20 kilometers. Now, if you make the parallel to the standard model, then if we miss with the shell by more than 5 centimeters or 10 centimeters, then we would say, good God, the standard model failed. we always hit with the accuracy of less than 5 centimeters or so. The accuracy is unbelievable. There are measurements that are done with accuracy of 8 or even 10 significant digits after the point. So it's the deepness and the vastness and the richness of the prediction that the standard model gives you is unprecedented.
I have a last question, I think. You mentioned space, okay? Do you picture space as having various attributes? If it's bending, then it has a shape also. It has a distance, I guess, extent. Do you think it has other attributes besides the way it's envisioned today?
Space is a very busy thing. I wish we understood it. I mean, I don't know whether you mean vacuum or space.
I probably mean space. It's the what we normally say space, merchav, okay, in Hebrew.
Okay. So,
which may or may not contain things. So when it doesn't contain much or anything, then it's vacuum. But the space is the infrastructure for the container.
So again, it's difficult a bit, but if you take two particles, then the force between them is going like, I mean, if it's a Coulomb interaction, it goes like 1/r². I mean, the closer they are, the stronger they attach each other. An electron has got no size. So basically you can bring an electron and a positron near each other to an infinitesimal distance. And therefore the force would go to infinity. So physics doesn't like infinities. We don't know what to do with that. So in order to avoid that, they went into superstrings. I mean, they try to assume that particle is not a point-like object, but a string-like object. And the theory, the math didn't work out till they had to go to 11 dimensions. Only at 11 dimensions, they could write a self-consistent math that would avoid the infinities at zero distance. Now we know that the space has got no 11 dimensions. You look at the corner of the room and you see 3. So it's clear that that's it. So the way out was to assume that there are additional dimensions, but they are sort of curved. If you look at the water hose, which from far away, then it looks like a line. But if you come closer, you see that it's a circle, and the dimensionality is more complex and bigger, higher. So the same holds true here. We have 3 dimensions which are standard. The time dimension, which is again a bit different than the spatial ones, and then the more dimensions which are smaller and curved, sort of loop-like or ring-like, all kind of shapes, and the geometry of that object is horrendous. I fear that there's a book by Green called The Elegant Universe, and he tries to explain it without the mathematics. The mathematics is very, very
difficult. Is it envisioned to have any other physical attributes, just being space? Like charge, like density, like
no
capacity. There are a whole bunch of things that happen in the physical universe. Does space have any of those attributes?
I don't think so. I don't think so. The vacuum is, but the space, no.
Great lecture.
Okay, so Prof, I just want to thank you so much on behalf of the WITS alumni here in Israel, WITS University, the South African main university in South Africa. We are the alumni here in Israel. So from WITS and from TELFED, South African Zionist Federation in Israel, and World Mizrahi, it's been really an honor and a privilege to have you on tonight. You really have shed a lot of light on the subject, the dark side of the universe. And to all our participants and our viewers who are going to be watching this YouTube, we just want to wish a happy Hanukkah and a happy festive season. And may the lights of Hanukkah and the lights of the festive season permeate with peace, happiness, health, and please God an end to the corona, and may we all be well and just have a good, healthy, and a good new year. So really, we want to thank you so much, Prof. It was an incredible talk, very illuminating, but it was phenomenal, and we are extremely grateful to you.
Thanks a lot, and
Thank
happy
you.
Hanukkah to everybody.
So, and all the very best, and Chag Sameach, and really thank you very much, Prof. We are really indebted to
Chag
you.
Sameach. Ehud, Ehud.
Thank you. Sorry for all my questions.
No, Larry, it's great. I mean, I know you.
And Larry,
Thank you very much.
thank you for connecting and organizing this wonderful.
Thank you, Chag Sameach.
My pleasure. Chag Sameach.
Chag Sameach, Ruti. Bonsoir.